This is the second part of my talk explaining how deconvolution can be used to analyse the renogram. In the first part I gave an introduction reminding you what a renogram is and talking about kidney transit time. Now in part 2 I'm going to discuss the theory of deconvolution, explain how it can be thought of as an idealised bolus injection renogram leading to something that we call the impulse response function. I'll give a graphical illustration of the processes of convolution and deconvolution and show how we can calculate mean transit time and subtract blood background. The problem that we're facing is that the renogram curve is a combination of three factors. It depends on uptake from the blood coming into the kidney, it depends on transit through the kidney, and elimination from the kidney into the bladder. So the uptake depends on the blood activity, and the blood activity varies with the speed at which we give the injection, the function of that kidney and the function of the other kidney, and recirculation of tractor that isn't taken up coming back into the blood for a second and third and fourth time. So the problems that we have to overcome are first of all that uptake and elimination are superimposed in the renogram curve, and then also we've got to allow for background activity. Now the deconvolution method tackles that by saying that the real renogram is the response of the kidney to a single intravenous injection, and that, as we've seen, results in a blood activity that's continually falling. But imagine what the renogram would look like if instead of giving an intravenous injection we gave a perfect bolus injection. It would have to be an injection straight into the renal artery, but if we give it intravenously, by the time it gets to the kidney it's no longer a tight bolus, it's already spread out. But also we'd have to make sure that there was no recirculation of any activity that came out of the renal vein without being extracted by the kidney, because that would come round in the blood for a second or third time and give us recirculation. So we don't actually need to give that perfect bolus injection into the renal artery, because the deconvolution method predicts what this perfect bolus renogram would look like based on the real renogram curve and the real blood curve, and manipulates those to predict what this perfect bolus would look like. So let's consider this simple model of the kidney. I'm going to think of the blood coming in through the renal artery and passing out through the renal vein, and at the glomerulus some pharmaceuticals can be removed from the blood and passed down through the renal tubules and mix in the renal pelvis before coming out down the ureter. So we can consider two regions of interest. The red region of interest is activity within the renal artery and renal vein, which is still within the blood. The green region of interest shows activity that's been extracted from the blood and is passing through the renal tubules and the renal pelvis, and that's the activity that we're interested in. It's been extracted from the blood. This represents uptake in the kidney, showing the kidney function. So if we give a nice little bolus straight into the renal artery, this yellow blob shows the activity appearing in the red region of interest. So the activity in that region goes up rapidly as the bolus comes in. Now at the glomerulus, some of the pharmaceutical will be extracted by the kidney and move into the tubules, and so it enters the green region of interest. So the amount coming in to the green region represents uptake by the kidney, and it's the fraction that's removed from the blood into the kidney that tells us how well the kidney is working. That's the function that we want to measure. But over the next few seconds the bolus will rapidly leave through the renal vein, so the activity in the blood drops back down to zero very rapidly, but it takes a few minutes for the activity passed down through the renal tubules, and during that time the activity in the kidney region of interest remains constant, so we get a constant activity in the kidney region representing transit down through the tubules. When it gets to the renal pelvis, the activity mixes with urine in the renal pelvis and gets diluted and gradually washes out of the renal pelvis, so the activity in the kidney goes down, representing elimination, decreases to zero. So we get a kidney activity that shows uptake and transit and then elimination, and this is the shape of what we would call the impulse response. It's the response of the kidney to this bolus input or impulse input, and it's convenient because it gives a rapid rise showing the uptake, a constant section showing transit, and a fall showing elimination. So it separates up uptake and transit and elimination, providing we give this perfect bolus injection. So the advantages of this impulse response or retention function are that it's the response to a standardized input. It's independent of the actual shape of the blood activity, so it removes the effect of recirculation and all these other organs. So the shape of the impulse response or retention function shows us an initial height here, which represents the uptake, and the duration here represents a measure of transit through the system and shows a distribution of the different transit times, and from that we can calculate the mean transit time. So we can use the impulse response function to measure the mean transit time, or the average transit time that it takes for a molecule to pass through the kidney. If we look at the distribution of transit times, we see that each of these lines here represents a different transit time through the system. So from the very shortest one here, which gets through the kidney quickly, to one here that takes a long time to get through the kidney. So the mean transit time is the average time for a molecule to pass through the system, so it's somewhere here on the distribution. MTT signifies the mean transit time. Now, if all the molecules took the same transit time, it would give the yellow area instead of the white area, and the definition of the mean transit time is when the white area and the yellow rectangle area are the same. Now, the yellow area is just a rectangle with a height equal to the initial height and a duration equal to MTT, so it's height times MTT. So if the height times MTT is equal to the white area, we can say that the mean transit time is just the white area, the area underneath the impulse response curve, divided by the initial height. So if we have this impulse response function, it's easy to calculate the mean transit time through the system. That's one reason why this impulse response function is such a handy thing to have. So we can see there that if we had this idealized renogram, life would be nice and easy. If we could achieve a perfect bolus blood activity which shows a spike that goes up and down, we would get this nice kidney activity which is an impulse response, where it's easy to interpret because we have uptake and transit and elimination all nicely separated. But to do that, we would need to achieve this perfect bolus, and that's not practical for several reasons. We could probably manage a very good, nice tight bolus injection, but to get it directly into the renal artery is quite invasive, and in any case there's no way we could avoid recirculation with activity that comes out of the renal vein without being extracted by the kidney. It's bound to come round in the blood for a second or third time unless we actually cut off the renal vein and drain the blood into a bucket. So this can be thought of as a nice idealized renogram, but certainly not one that we can achieve in practice. But the real renogram follows off from an intravenous injection where we've got slow recirculation and the blood activity persists. So instead of having the nice bolus, we have this long persisting activity. So the question is, what would the real renogram look like in response to that? We can answer that question by representing a continually falling blood curve as a series of bolus inputs, one after the other, like that. So if we assume that the first minute, for example, is an input of 100 units of activity, and we assume that we have 50% uptake in the kidney, then we will have 50 units entering the kidney. The other 50 units comes out through the renal vein. And if we also assume that there's a transit of about 3 minutes during which the activity transits through the tubules and then it eliminates over the next 2 minutes, we get an impulse response like that, with the uptake a 3-minute transit and then elimination. So that's the response of the kidney to the first minute of input. We can then consider the next part of the blood curve to be another bolus of 70 units 1 minute later. Now if we also assume we get 50% response to that, we get 35 units entering the kidney, and it still takes 3 minutes to transit and then eliminate over the next 2 minutes. So the shape of this yellow curve is the same shape as the white one, but it's slightly smaller because the input was smaller, and it's also delayed by 1 minute because the yellow input was 1 minute later than the white, so the yellow response is 1 minute later than the white. Now we've made two assumptions there. We've assumed that the system is linear. In other words, this 50% response always applied. If we double the input or halve the input, we still maintain a 50% uptake. We're also assuming that it's stationary. The response doesn't change with time, so that if the white input gave something of this shape, the yellow input later gives something of the same shape. So no matter what time the input comes, it is the same shape, just delayed. Those two assumptions are important, and I'll come back to them later in the talk. But if we just add that yellow response onto the white response, we get the total response to the yellow and white, something like that. We can now consider the third minute, which is also somewhat smaller, say 50 units in the blood, but if we still get a 50% response, then we expect 25 units appearing in the kidney. Again, is delayed by 1 minute, but the shape is the same, and we can add that in. Now the fourth minute is a bit smaller, but it's the same shape, and we add that in, and so is the fifth, the sixth, and the seventh. So if we add all those in, we see that we get a response made up of lots of individual responses of this shape. So a continually falling blood curve like that gives a response of this shape, which is indeed quite like a real renogram shape. So this is a way of determining what the renogram shape would be like, what the kidney response would be like for a real blood input based on this assumption of the impulse response. Now mathematically, that method is called convolution. What we're really interested in is the opposite, deconvolution. So to apply that process in reverse, we have an observed blood curve which we can assume has got a decreasing number of units of activity with time, and an observed renogram with a shape like this. Now if we observe the first minute of the blood curve to have 100 units of activity, and the first unit of the renogram to have 50 units of activity, we can see that in this model that is pure white. So this is the response to the first minute, and comparing 100 with 50, we can see that we get a 50% response. So we can assume that we also got 50% of the 70 yellow there, giving us 35 yellow there, 50% of the purple 50 there, giving us 25 there, 50% of the 36 red, giving us 18 red there, and 50% of the 24, giving us 12 there. So that allows us to know exactly how big these top segments were, and we can take those off and throw them away. And now in the second minute, that exposes another pure white, which is also 50. So once again we see we had a 50% response in the second minute. So 50% of our yellow there is 35, 50% of our purple there is 25, 50% of our red 36 is 18, and 50% of our green 24 is 12. So once again we can predict the height of these units and subtract those. Once again it uncovers a 50% white there, so once again we can say that 50% of our yellow 70 is 35, 50% of our purple 50 is 25, 50% of our 36 is 18, and so on. So once again we can throw away the top unit there. Now it turns out that we expose a white which is 40. So now we see at the 4th minute we have a 40% response. So 40% of our yellow 70 there is 28, 40% of our purple 50 there is 20, and 40% of our red 36 is 14. So once again we can throw those away. So bit by bit we're able to subtract all the extra little bits of the renogram, and we're left with just the white, which is our impulse response, 50 units for the first 3 minutes, falling over the next 2 minutes. So that's how we can apply deconvolution to undo the renogram, to get from the renogram to this, which is what we wanted to look at, the perfect bolus response. So to illustrate that graphically, we can think of convolution as the process of starting off with this perfect bolus input with a known response consisting of uptake and transit and elimination, and gradually build up from that what the response would be to an input that was falling in time, like the blood activity. That gives us the renogram, which is this shape, from the mathematical process of convolution. Deconvolution is the opposite, where we start with a known blood activity that is decreasing with time and a measured renogram that has this shape, and from that we subtract away a bit at a time all of the elements until we're left with just the impulse response, showing the uptake, the transit and the elimination, which is the theoretical response to this bolus input. If you're interested in the mathematics of this, then you can find more details in the chapter written by David Sutton on deconvolution of the renogram, which appears in Mathematical Techniques in Nuclear Medicine, which was IPM Report 100, published in 2011, or in my review article on application of mathematical methods in dynamic nuclear medicine studies, which appeared in Physics and Medicine and Biology in 1999. So mathematically we can write R of t as the renogram as a function of time, I of t the blood input as a function of time, and H of t as the impulse response. In that case, R of t, the renogram, is a convolution of I and H, where star means a convolution. We can write the same thing in discrete form, as where Ri is the ith time interval of the renogram, Ij is the jth time interval for the blood input, and H is the impulse response, and delta t is the time interval between points. In that case, this summation is the equivalent way of writing that convolution. So to solve it, there are several approaches. The most common is to use the matrix method, which is just what I've illustrated graphically in the previous slides. Mathematically, it's written as the inverse of this equation, so you can see that we get the ith time point of the impulse response by taking the ratio of the renogram response to the first point of the input, and subtracting some fraction of the product there one at a time to gradually take them off, as I show graphically. An alternative approach is to use the Fourier transform, where we use the fact that the Fourier transform of a convolution is the product of the Fourier transforms of the components. So if we take this convolution and take the Fourier transform, that would give us that the Fourier transform of R is equal to the Fourier transform of I multiplied by the Fourier transform of H. And if we rearrange that, we get H to be the inverse Fourier transform of the ratio of the Fourier transforms of the renogram and the input function. Whichever method we use, it's all rather subject to noisy data. Here we are taking a ratio of two rather noisy values and using that to subtract something off, which means that any errors will propagate and get worse and worse each time. If we use the Fourier transform method, then we're dividing one rather noisy function by another, and that can also amplify noise. So a better method is to use a constrained optimization technique where you find a smooth solution that is consistent with the noise. That's a more sophisticated way, but whichever method you use, you have to be very careful to allow for the fact that the data is rather noisy, and that tends to blow up and amplify any small errors. So the teaching point to remember about this is that convolution is the process of calculating the response of a system to a real input when you know its impulse responds to a perfect bolus input. Deconvolution is the reverse. It's the process of calculating the impulse response of a system when you know its response to a real input. And it's deconvolution that's relevant to the renogram, because we know the input from the blood curve and we know the response, which is the renogram, and what we want to calculate is the impulse response to a perfect bolus. So the impulse response is easy to interpret once we've got it, because the initial height represents uptake, the duration represents transit, and the downslope represents elimination. So it's much easier to interpret than the actual renogram itself. So far we've been talking about what happens without any background in the renogram, assuming that background already been subtracted. And we saw that the real renogram is a blood curve that falls with time, and that leads to a kidney response, which is a curve something like this. If we were able to give this perfect bolus input, we would get a spike in activity for the blood, and we would get this idealized renogram, which was uptake, transit and elimination. That is the impulse response function. But we don't need to do that, because by applying deconvolution we can predict this impulse response by the mathematical technique without actually having to give that bolus injection. So that's the situation without any black background. If we consider the same situation with background, then we get blood activity that's falling with time, and the blood background on the renogram is also falling with time, and the renogram sits superimposed on that, so the renogram is even more complicated to interpret. If we did the same thing with our bolus injection, we'd now get our blood activity as just being the spike of activity. The idealized renogram is still the same response in the kidney, but the blood background is now a spike at the beginning, because that's all that the blood activity was. So we get something like this. So we still get the same shape for the kidney response, but we get this little bit sitting on the top. So deconvolution can still predict this idealized renogram, but it's now easy to remove the background, because if we can find the plateau here and chop that off, we can just throw away the background, which is all concentrated as a spike at the beginning. So not only can deconvolution give us the impulse response and calculate the mean transit time, it also turns out it's a way of removing blood background. So in summary, deconvolution gives the renogram that will be obtained if an idealized bolus injection could be given straight into the renal artery with no recirculation. We can't do that in practice, but mathematically it will simulate that, and the impulse retention function that we get shows uptake as the initial height, transit here, and in particular we get the mean transit time from here to here, and the blood background is now concentrated as a little spike at the beginning, which we should be able to isolate and subtract off. So that's the theory. In part 3 I'll go on to show how deconvolution can be carried out in practice.